Hello. If you got the chance to do the exercise from the previous lecture, you would see that certain linear maps, such as rotations, reflections, and so on, changed the given vector. So if we had a vector like this, for example, and then we applied a transformation, let's say t, then the resulting vector might be some different vector like this. Okay, so in the exercise, you looked at different transformations being applied to different vectors, and you could see the difference between the input vector and the output vector. So we can represent this as t acting on a vector v gives us a new vector v prime. Okay, so that is the typical behavior of a transformation. You have an input vector, it gets changed via t to some output vector. Now, in certain situations, we might have the following. T acting on a vector v is a multiple of the vector v. Okay, so this transformation might have the action of changing the vector for some given vector, but there are special vectors whereby if you apply the transformation, it just scales the vector. Okay, so this is for a special subset of vectors, and those are called eigenvectors. So the special subsets of vectors that are simply scaled by the transformation they are called eigenvectors. Yeah. And then the scaling amount lambda, this is called the corresponding eigenvalue. Yeah, so we have eigenvectors and corresponding eigenvalues. Now, given a particular transformation or particular linear map, we would like to find what are these eigenvalues and eigenvectors. Okay, so we start by trying to find a way of working out what these eigenvalues and eigenvectors are, and then we'll see what we can do with them. Okay, so they have pretty nice applications. So let's start with the equation for an eigenvalue and eigenvector and work out how we can calculate what they are. So we start off with t acting on v gives us lambda v. Okay, so that's the definition of an eigenvector. Okay, it gets scaled by t. Okay, so we can take this right-hand side over to the left-hand side. So we get t of v is equal to minus lambda v is equal to the zero vector. Yeah, so I'm just going to write 0, but you can put in the 0 vector if you wish. Okay, now this lambda times v, I can multiply that by the identity and it won't do anything. So t of v minus lambda I v is equal to 0 still. So multiplying by the identity didn't do anything there. Now this v we can factor out onto the right. So we end up with t minus lambda r times v is equal to 0. Okay, so we have this matrix in front here. Let's call this A. So this is A. We have A times v is 0. Okay, so this is the equation that we would like to solve, okay, because we want to solve for these solutions v. However, if A is invertible, then we can multiply both sides by the inverse, and then the only solutions we'll get are the 0 vector as the solution, which is not very interesting. We don't want the zero vector as an eigenvector. Yeah. So the only option we have is for A to be non-invertible or singular, and in that case, we get non-zero solutions. So if A is invertible, or non-singular, then the only solution is the zero vector. Okay, and then just a note, we don't want the zero vector to be counted as an eigenvector. So we don't want the zero vector to be an eigenvector. Okay, so we left with A being non-invertible, and then that gives us non-zero solutions. So if A is not invertible, then we have non-zero solutions, which is good. Okay, and then the sets of these solutions we call the eigenvectors. Okay, so when would this A be non-invertible? Well, when the determinant is 0. So the determinant of t minus lambda r, that must be 0. So we set the determinant of t minus lambda r to be equal to 0. And then this gives us a polynomial after taking the determinant, which we call the characteristic polynomial. So after taking the determinant, we get a polynomial called the characteristic polynomial. Okay. So once we have this characteristic polynomial, it's a polynomial in lambda, okay, because everything else there are just constants. Lambda is our variable. So we get a characteristic polynomial in lambda. The roots of that polynomial we call the eigenvalues. The roots of the characteristic polynomial are called the eigenvalues. Okay. So once we have the eigenvalues, we can take those eigenvalues, substitute them back into our previous equation over here, and then solve this equation for the eigenvectors v. Yeah, and we need to do that for each of the possible eigenvalues. Okay, so then we get these pairs of eigenvalues and corresponding eigenvectors. Okay, so let's have a look at an example. Okay, so we want to find the eigenvalues and eigenvectors of the following matrix. So 1, 2, 0, minus 1. Okay, so simple 2 by 2. And we'll see if we have a 2 by 2 equation, then the characteristic polynomial will be quadratic. If we had a 3 by 3 matrix, then the characteristic polynomial will be cubic. Okay, so let's go. So what we want is the determinant of this matrix. So 1, 2, 0, minus 1, minus lambda times the identity. So in this case, the identity will be the 2 by 2 identity, and we want this to be 0. Okay, that's how we get our non-zero solutions from this. Okay, so let's put everything together, and then we end up with the determinant of 1 minus lambda, then 2 minus 0, so that's just 2, 0 minus 0, that's still 0, and minus 1 minus lambda, so that's minus 1 minus lambda. Okay, we want this determinant to be 0. So if we do our multiplication, we end up with 1 minus lambda, minus 1 minus lambda, and then minus 0 is equal to 0. We can ignore that minus 0 over there. So we end up with 1 minus lambda, 1 plus lambda, if we take out the minus there, equals 0. Okay, and this gives us 2 possible solutions. So let's call lambda 1 to be the first solution, which is 1. And the second solution, for the second bracket there, it will be minus 1, so lambda 2 equals minus 1. So those are our 2 possible eigenvalues. Okay, now corresponding to each eigenvalue, there is an eigenvector. You might get 2 eigenvectors per eigenvalue, but we will talk about that later. Okay, so how do we find that? Well, we just substitute it back into our equation that we had above here, and then we can solve for the eigenvector. Okay, so we're going to have our original matrix, 1, 2, 0, minus 1, minus lambda, but lambda 1 is just 1, so we can leave that. And then the identity, 1, 0, 0, 1. And then it's this times the eigenvector is equal to 0. Since this is 2 by 2, so we're working in 2 dimensions, we can write it as just xy. Okay, for some undetermined xy, we don't know what it is yet. And this must give us the 0 vector, so we can write that as 0, 0. Okay, so the goal is to find x and y. Okay, so let's clean this up a bit. So this is going to give us 1 minus 1, that's 0, 2 minus 0, that's just 2, 0 minus 0, that's 0, minus 1 minus 1, that's going to be minus 2. Times xy equals 0, 0. And now an important note, we can do row operations on the system and it won't change the solution. Okay, so that's a very helpful note. Row operations won't change the system solutions. Okay, which is very nice because we can simplify this, simplify it down, and then that makes it easier to solve for x and y. Okay, so in this case, we don't really need to do too much. We can just write this as 0, 1, 0, minus 1, or we could just leave it as 0, 2, and 0, minus 2. In this case, it's very simple, so we don't need to. Times xy is equal to 0, 0. Okay, so what do we have here? We have, if we look at the first equation here, we have y is equal to 0. And in the second equation, we have minus y is equal to 0. So in both cases, we have y is equal to 0. So this system, or this matrix equation, okay, so you can treat it as a system of equations or a single matrix equation, tells us that y equals 0. Okay, that's good. So we have one of the solutions, but it doesn't tell us anything about x. In other words, there's no restriction on x. Okay, so x can really be anything. So that means that we don't have a single eigenvector, but we have a whole set of eigenvectors parameterized by x. So we can write the whole set of eigenvectors, which we call the eigenspace, is equal to the set of all x and 0, such that x is an element of the complex numbers, because we work in the field of complex numbers. Yeah, like that. Because again, there's no restriction on x. X can be any complex number. Okay, so that gives us the full eigenspace. Now, instead of writing it like this, we could also write it as the span of 1, 0. Okay, because that's exactly what this set is. X can be any complex number. In other words, we can write it as any multiple of the vector 1, 0. Yeah, it has the same meaning. So any multiple of 1, 0. Okay, so those are all the possible solutions. Now, if we just want a single eigenvector, we can pick any of those. They'll satisfy the equation. But what we usually like to do in physics is pick a normalized eigenvector. So out of all of these possible eigenvectors here, we pick the one that has norm of 1. So we pick the normalized eigenvector. Okay, so in this case, out of all the possible multiples, the normalized one, let's call it V1 to go with lambda 1, is just 1, 0. Okay, now 2, 0 is also a possibility, but that's not normalized, so we're not interested in that. Okay, so normalizing these eigenvectors in maths is not really needed because we have the full eigenspace. However, in later on when we do quantum mechanics, we would like to work with normalized eigenvectors. Okay, because those will correspond to normalized quantum states. Okay, don't worry too much about that now. We'll get to it later. But it is better to work with normalized eigenvectors. Okay, so that's how we find the first one. We can do a similar method. Okay, so we take lambda 2 equals minus 1, substitute it in, solve for x and y, and then we get the eigenspace. So we can do a similar thing for lambda 2. And we get V2 corresponding to lambda 2. If we normalize it, like we want to do, is 1 over root 2, 1 minus 1. Okay, so that is the second eigenvector. Okay, so this was a pretty short example on how to find the eigenvalues and eigenvectors for a 2x2 matrix. Doing this for a 3x3 matrix is very similar as well. Okay, instead of a quadratic characteristic polynomial, you will have a cubic. So you can have up to 3 distinct eigenvalues, and then you can find the corresponding eigenvectors. Okay, so there's a few exercises in the notes. Please try them out. If you have any issues with them, just email me, or you can visit me in my office, and we can go through it together. Okay, so let's look at one of the applications of eigenvalues and eigenvectors, and that is diagonalization of matrices. diagonalization of matrices. Okay, and we will be using this quite a bit in quantum mechanics. Okay, the reason being is that diagonal matrices are often a lot easier to work with than non-diagonal matrices. Okay, so what we want to do is take a given matrix where the elements are all over. Okay, so we can have something like 0, 1, minus 2, 0, 1, 0, 1, minus 1, 3. Okay, so this is a non-diagonal matrix. We've got elements all over the place there. What we want to do is instead replace this with an equivalent matrix. So we can do all the same things with it. However, it has a different form, which is diagonal. So we have 1, 0, 0, 0, 1, 0, 0, 0, 2. Okay, so these are equivalent, okay, up to a certain transformation, of course. But the one on the right will be a lot easier to work with because of its diagonal form. Okay, and we'll see that we're going to be needing that later on when we do functions of matrices. Okay, so if we apply a function to a certain matrix, we'll see it's a lot easier to do if it's in diagonal form. If it's not in diagonal form, we need to do this process of diagonalization, bring it into diagonal form, and then we can apply the function. Okay, so that is the major application for this eigenvalues and eigenvectors and diagonalization. Okay, so let's see how we do this. So the way this is done is by using a matrix transformation. Okay, so we know how to do vector transformations. We take a vector, we multiply it by a matrix, and we get ourselves another vector that's been transformed. When we're dealing with matrix transformations, it's fairly similar, but instead of vectors and matrices with one-sided multiplication, we do a two-sided multiplication. Okay, so what do I mean by that? I mean, if we have a matrix A, we can write this as a diagonal matrix D via A equals P, D, P inverse, where D is the diagonal matrix. Okay. In other words, a non-diagonal matrix A can be represented by a diagonal matrix D, provided you transform it with these P and P inverse matrices. Okay, and then this is entirely equivalent. If we take the P's over to the other side, we can write it as P inverse A P is equal to D. Okay, so maybe on the right-hand side, you can see the transformation a bit easier. You've got A, you transform it via P inverse and P, and you end up diagonalizing it. So in both cases, D is a diagonal matrix. Okay, so we're going to see how do we do this transformation process. Yeah, and we're going to do it via an example. Okay, so this example will show how do we construct P and how do we construct the diagonal matrix D given A. Okay, so let's say A is equal to 0, 1, minus 2, 0, 1, 0, 1, minus 1, and 3. Okay, so we would like to diagonalize it. So this comes in 4 steps. So step 1. calculate the eigenvalues and eigenvectors of A. Okay, so calculate the eigenvalues and eigenvectors. Okay, so I'll leave that as a homework problem. Okay, but we end up with the following. Lambda 1 is 1. Lambda 2 is also 1. And lambda 3 is 2. Okay, so just because we have a cubic doesn't mean we're going to have 3 distinct eigenvalues. We might have copies like this here. Okay, once we have that, we can calculate the eigenvectors. So we can have V1 is going to be 1, 1, 0. V2 will be 0, 2, 1. And V3 will be 1, 0, minus 1. Okay, so these are not normalized. Okay, so when diagonalizing a matrix, you don't need to normalize them. But when we're doing quantum mechanics and we want to work with state vectors, then those do need to be normalized. Okay, so that's the only case where we insist on normalizing the vectors. When you're working with other applications like this, you don't have to worry too much about normalizing. Okay, so once we have that, we have step 2. Construct the P matrix using the eigenvectors as the columns. Okay, so now I need to tell you that this numbering here is quite important, because when we arrange the columns, we need to remember the order. So here we've got lambda 1, lambda 2, lambda 3, V1, V2, V3. Once you've labeled them in that order, please stick with that order. Okay, so we've got P is equal to, we're going to use V1 as the first column. So 1, 1, 0. V2, that will be the second column, 0, 2, 1. And V3 is 1, 0, minus 1. Okay, so it doesn't have to be in that precise order. You can move them around. But once you've picked the order for the columns, you need to stick with that. Then you need to remember which ones went where. Okay, so once we have P, we then need to calculate the inverse of P. So that's step 3. Okay, step 3, calculates the inverse of P. Okay, so it's a 3 by 3, so it's not too easy, but not too difficult either. So again, I'll leave that as a homework exercise. P is equal to 1, 0, 1, 1, 2, 0, 0, 1, minus 1. This gives us P inverse is equal to, Yeah, so from this, we find P inverse. Okay, now P inverse will exist, so you don't need to worry about finding the determinant. But if I give you an arbitrary, if you find like an arbitrary matrix and you try to diagonalize it, then check if you can invert it, because not all matrices can be diagonalized. Okay, so of course the ones in the exercises and the ones in the assessments, they can be diagonalized, so P inverse will exist. But if you just make up a matrix, it may not be diagonalizable. Okay, so just be a bit careful with that. Okay, so step 3, calculate the inverse of P. And then step 4, we can write the diagonal form D is equal to P inverse AP. Okay, so this you can calculate this. So P inverse AP, you can substitute the matrices that you found and then find D, but there's an easier way. D is the diagonal matrix where the diagonal elements are in fact the eigenvalues. So we have 1, 0, 0, 0, 1, 0, 0, 0, 2 in that order because we chose V1 to be the first column, V2 to be the second, V3 to be the third, which means the corresponding eigenvalues 1, 1, 2 are also matched up column-wise. Okay, so the first one is 1, the second one is also 1, and the third one is 2. Okay, so if you swapped the eigenvectors, then these eigenvalues would also be swapped. Okay, but will always be diagonal. Okay, so then this is equal to P inverse. So again, that's for homework. 1, 0, 1, 1, 2, 0, 0, 1, minus 1. Inverse times A, which was 0, 1, minus 2, 0, 1, 0, 1, minus 1, 3, and then times P. That was 1, 0, 0. 1, 1, 0. 0, 2, 1, and 1, 0, minus 1. Okay, so you can check this for yourself. Do matrix multiplication for the right-hand side, and you should get the left-hand side. So check for yourself. Okay, so matrix multiply the right-hand side to see if you get the left-hand side. Okay, so I'll leave that for homework as well. Okay, so this is a bit long to do if it's a 3x3 matrix, okay, because finding the eigenvectors, that can take a bit of time. Finding the inverse, again, that can take a bit of time, but it's not too bad. In the exercises in the notes, those are 2x2 matrices. Okay, so you still get the practice on diagonalizing, but it should be a bit quicker. Okay, because finding the inverse in those cases is a lot easier to do with a 2x2 matrix. Okay, so that is the process of diagonalizing a diagonalizable matrix. So just note again, don't just make up your own matrix and try to diagonalize it. It may not always work. Stick to the matrices that I provide, or you can Google diagonalizable matrices, and then you should get some examples there that you can work with. Okay, but there's quite a few exercises in the notes as well that you can go through. Okay, so just diagonalizing a matrix, that is a pretty nice application of eigenvalues and eigenvectors. But the real reason that we do this diagonalization process is to take functions of matrices. Okay, and we're going to be seeing that in quantum mechanics. Okay, so we're going to have a matrix, which we will call an operator, and then we need to take certain functions of these matrices to get back a matrix. Okay, so let's have a look at that. Okay, so functions of matrices. Okay, so let's say we have a function f of x, and this is equal to sine of x, where x is, let's say, a complex number. We know how to work with that. Okay, so this is well defined. We can calculate this for any complex number. Everything is fine. But then what about the following? So if we have f of a matrix, let's say -4, 2, 6, 7, what does this mean? How do we take this matrix and substitute it into the sine function? That doesn't really make any sense. Okay, but we'll see that we can make some sense of this by representing the function as a Taylor series. Okay, so that's a little bit of a spoiler. Let's start off by taking a matrix and finding simple powers of the matrix. Okay, so we can imagine that as f of x equals x to the n. Okay, so we know how to multiply matrices. So finding powers of matrices, where the powers are integers, that should be pretty simple. It's just repeated multiplication. Okay, so let's have a look at this simple case first, and then we will look at the more complicated case afterwards. Okay, so we'll try to keep this as simple as possible. Let's start off with a diagonal matrix D, which is given by lambda1, 0, 0, lambda2. Okay, so these may not be eigenvalues, okay, but we will see later on that when we work with diagonal matrices, they will be the eigenvalues. Okay, but for now, just treat them as just regular numbers. Okay, so what we want to do is find d squared, okay, as a starting point to find higher powers of d. Okay, so d squared, what's this going to be? So let's just calculate it with matrix multiplication. So we have lambda1, 0, 0, lambda2, and then times itself. So lambda1, 0, 0, lambda2. Okay, so multiplying this out, we get lambda1 squared, then 0, 0, lambda2 squared. Okay, so this looks like if we're taking the square of a diagonal matrix, it squares the diagonal elements. Okay, so just a little thing to think about. Okay, so we haven't proved any of this yet, but it looks like squaring a diagonal matrix is the same as simply squaring the diagonal elements. Okay, and this is in fact true. So you can prove this using induction. I think we'll leave that as a homework problem. So some more homework. So prove that if d is equal to lambda1, 0, 0, lambda2, then d to the n is equal to lambda1 to the n, lambda1 to the n, 0, 0, lambda2 to the n. Okay, so that's quite simple to do using induction. Okay, so very quick homework problem. Okay, so once you've convinced yourself of that, we can look at taking functions of matrices. So since we can do powers of matrices, why don't we take the matrix and substitute it into the Taylor series? Because the Taylor series is just powers of x. So we can replace x with the matrix, and we can take powers of matrices. So we should get some result from that. Okay, so recall that f of x can be represented using a Taylor series or in this case, Maclaurin series, but don't worry too much about that. So we have k equals 1 to infinity. We take the kth derivative, evaluated at 0, over k factorial, x to the k. Okay, so Taylor series centered at 0, or Maclaurin series. Changing this is very simple. We just shift x, okay, and then evaluate the derivative at that point. So don't worry too much about that. So what we're going to do now is, instead of x being a complex number, we're going to substitute a matrix. Okay, because on the right-hand side, we're just taking simple powers of x, and we've just proven that we can take powers of diagonal matrices. So that allows us to substitute a matrix on the left-hand side for some arbitrary function, provided it has a Taylor series, of course. So all we do is we just substitute d, and that gives us the sum from k equals 1 to infinity, if k evaluated at 0 over k factorial, d to the k, and we can calculate that. So this gives us meaning to taking a function of a matrix. So we want to do the left-hand side, taking just the function of a matrix, but instead of doing that, we're going to do this right-hand side by substituting into the Taylor series, again, provided it exists. Yeah, and that gives us meaning to taking the function of a matrix. Okay, so let's do this. Let's substitute in our matrix. So this is going to be equal to the sum from k equals 1 to infinity, f k at 0 over k factorial. And then we know this is going to be lambda 1 to the k, 0, 0, lambda 2 to the k from our previous work over here. Okay, but the summation we can take inside the matrix. Okay, and the constant we can take inside. Okay, all of that's fine. So this becomes the sum from k equals 1 to infinity, f k at 0 over k factorial, lambda 1 to the k, 0, 0. And then we have the same series here, k equals 1 to infinity, f to the k, 0 over k factorial, lambda 2 to the k. Now, of course, we are neglecting all the important maths behind this. So the idea of taking the series inside the matrix and talking about series convergence and all of that, we're going to ignore all of that and just assume we can do it. Okay, so that's mainly how physics goes. We just assume that the series converges and we can do all these nice things with it. Okay, but it is important in the back of your minds, just think about what we're actually doing here. Okay, so messing around with these series like this, there are certain things that we need to keep in mind. Okay, with convergence and all of that. Okay, now this first series in the first row, first column, that is just the Taylor series, but evaluated at lambda 1. Now, since this is the Taylor series for f, we can write this as f of lambda 1. Okay, 0, 0. And then the second series, that's just f at lambda 2. Okay, and then remember on the other side, we had f of d. Okay, so here we get the first important result. If we have a diagonal matrix D, then applying the function to it is the same thing as applying the function to the diagonal elements. This is very similar to what you will prove later, that if you have powers of the matrix, that is the same thing as powers of the elements. Okay, so lambda 1 squared, lambda 2 squared, but this is even more general for an arbitrary function with the Taylor series. Taking the function of the matrix is the same thing as taking the function of the diagonal elements. Okay, so that's good. However, we are going to be working with matrices that are not diagonal. Okay, so we're going to start off with some arbitrary matrix, A, and we want to take the function of it. How do we do that? Well, we'll see that this idea of diagonalization makes it very easy to do. Okay, so let's say we have a diagonalizable matrix A, and we want to take powers of it, right? Because we need to substitute it into this, this expression here. So instead of d to the k, where d is diagonal, we want an arbitrary matrix A to the k. Okay, so let's have a look at how we're going to do that. So we assume A is diagonalizable. In other words, we can write A as PD P inverse. Now we want to calculate powers of A. Let's start off with A squared, just as an introduction, so A squared. Now on the right-hand side, we need to square that. But with matrix multiplication, that's very easy because we just write that expression down twice. So it's going to be P D E inverse times itself, so P D E inverse. Now, matrix multiplication is associative, so these brackets can be moved around. So let's do that. So A squared is going to be P D, open bracket, P inverse times P, close bracket, D P inverse. But P inverse P is the identity. So this is going to be A squared is equal to P D times the identity, but we can leave that out, times D times P inverse. So A squared is equal to P D squared P inverse. But note that we took the power of A, but that only has an effect on the powers of D. The P and the P inverse, they stay on the left and the right, unaffected by it. Okay, because of that P inverse P relation here. And in fact, this works for any power. You can show that by induction again. So A to the K is P D to the K P inverse. And if we can take arbitrary powers of K, then we can take functions of A via the Taylor series. So through a very similar argument that we had before with D, we can take f of A is equal to P f of D, which we know how to do now, P inverse. So we know how to deal with this. Yeah, and that allows us to take functions of diagonalizable matrices. Okay, so let's have a look at a quick example of taking the exponential of a matrix A. Okay, and there's a few more exercises in the notes as well. You can try that out. Okay, so example, we want to find e to the power of minus 1, 2, 0, 3. Okay, so how do we do that? Well, the first thing we need to do is find the eigenvalues and eigenvectors so that we can diagonalize the matrix. Okay, so we need to find the determinant of minus 1 minus lambda, 2, 0, 3 minus lambda, and we want that to be 0. Okay, multiplying this out, we're going to get 1 plus lambda, 3 minus lambda is equal to 0. This gives us two eigenvalues. Lambda 1 is equal to minus 1, and lambda 2 is equal to 3. Okay, good. Now that we have the eigenvalues, we can find the corresponding eigenvectors. So substituting in the minus 1 for the first one, we're going to get 0, 2, 0, 4. times some xy, we don't know what it is yet, is equal to the 0 vector. Okay, this is equivalent to, so this is equivalent to 0, 1, 0, 0 times xy is equal to 0, 0. Okay, just via row operations. Yeah. Of course, the original matrix is very simple on its own, so you don't need to do this, but it doesn't hurt. Okay, so this gives us that y is equal to 0 and x is free. Okay, there's no restrictions on x. Okay, from the system here. Okay, which means we can write the first eigenvector v1 as 1, 0. Okay, and that's from the span of 1, 0. But again, we can just choose a particular one. This is a pretty simple choice. Okay, and then this is with lambda 1 is minus 1. We can do the same thing with lambda 2. So substituting that into the equation gives us minus 4, 2, 0, 0 times a different xy. That's 0, 0, again, from that equation we had earlier. Okay, we can simplify this, again, using row operations, but this is already simple, so you don't need to, but if you want to, that's fine as well. So we can simplify this to 2 minus 1, 0, 0, xy equals 0, 0. And from this, we get two equations. The second one is not very interesting. It's just 0 equals 0, so that doesn't help. The first one gives us 2x is equal to y. Okay, so what we can do is say one of them is a particular value, and then we can solve for the other. So if we set x to be 1, then y is going to be 2. Yeah, and of course we could have chosen x to be anything because we're working with the span of the vector, but that's just the simplest thing to work with. Okay, so this gives us v2 is equal to x is 1, y is 2. And of course, any other multiple works as well because it will be in the span, but we want to make things as simple as possible. Okay, and then this is with lambda 2 is 3. Okay, so we've got our two eigenvectors and the two eigenvalues. We can now diagonalize the matrix A. So A, remember, is P, D, P inverse. We know what P is because we've got the columns of P. Those are the eigenvectors. And we know what D is because those are the eigenvalues. So this is going to be 1, 1, 0, 2 times D, that's just the eigenvalues, minus 1, 0, 0, 3. If you ever confused about which ordering you should pick, the one that I'm going to go with is to have the eigenvalues arranged in ascending order. Okay, so lambda 1 should be the smallest, lambda 2 should be the next biggest, and so on. So when you're solving your characteristic polynomial, organize it like that, and then everything should follow from that order. Okay, of course, you don't have to do it like that, but that's the way that I'm going to do it. Okay, and then 1, 1, 0, 2, so that's P, but we need to find the inverse. Okay, so this is going to be 1, 1, 0, 2 minus 1, 0, 0, 3. And the inverse, we can calculate that pretty easily because it's 2 by 2. That's going to be 2 minus 1, 0, 1, and then divided by the determinant, but that's just going to be dividing by 2. So we can times by 1/2. Okay. Once that is done, we can then find the exponential of this by exponentiating the diagonal matrix in the middle there. Okay, so this implies that e to the a is going to be 1, 1, 0, 2. And then we just have e to the minus 1 for that middle bit. 0, 0, e to the 3. Yep. And then times that other part there. The 2 minus 1, 0, 1 times a half. Okay, so we have exponentiated that diagonal matrix in the middle. All we need to do now is multiply everything together if we want this to be a single matrix. Okay, that's pretty easy to do. It's just matrix multiplication with 2 by 2 matrices. And we end up with e to the minus 1 minus 1/2 e to the minus 1 plus 1/2 e to the 3, 0, and e to the 3. Okay, so not the nicest looking matrix, but that is the exponential of the matrix A. Okay, so the bulk of the work for taking functions of matrices is diagonalizing the matrix. So once you've diagonalized it, taking the function is just taking the function of these elements in the middle matrix. Okay, and then if you want to have a single matrix in the end, it's just the matrix multiplication. Okay, so I'll leave the other two as homework. Sorry, the other two from the exercises in the notes, and then we can go through that together another time. Okay, so that's it for this lecture on eigenvalues and eigenvectors. Okay, so there is a lot more theory with eigenvalues and eigenvectors. You'll cover that in your maths module. Yeah. But we won't do that just because of time. Okay, so this is just a brief introduction, and that's more than enough to cover the quantum mechanics part that we're going to be doing in the next chapter. Okay, but if you do have more questions on eigenvalues and eigenvectors that we didn't cover, so if you're interested in more stuff, please don't hesitate to ask as well. Okay. So your questions don't have to be strictly related to what we're doing. They can be more general if you want. All right, so in the next lecture, we're going to be looking at two types of matrices called Hermitian matrices and unitary matrices. And we're going to be looking just at a brief introduction to them so that we can understand the quantum mechanics for the next chapter. Okay, so there's a lot more that can be said about Hermitian and unitary matrices, but we're going to do a brief introduction. Okay, as always, if you have any questions, please don't hesitate to email me whenever you like. I'll get back to you as soon as possible, or you can visit me in my office. The details are on the course webpage. Okay. And please remember the tutorial 2 will be due on Monday, as well as the assignment. So please look at the due dates and times for that. Okay, if you still have questions on the tutorial or assignment, please ask as well. Okay, I'll see you next time.